Today on Flipping Science, we're talking about isotopes. So the science understanding we're going to look at is the atomic number and mass number provide information about numbers of subatomic particles in an atom, and that many elements consist of a number of different isotopes which have different physical properties but have the same chemical properties. And then we're going to represent isotopes using the right notation. So what is an isotope? So an isotope is when we're comparing two atoms, they have the same atomic number but they have a different mass number. And the reason why they have a different mass number is because they have either more or fewer neutrons than a regular atom would have. So let's talk about hydrogen, for example. So most hydrogen, if we looked at the hydrogen nucleus, there's a proton, and then if we look at the electrons, we've got one electron zooming around it like that. So that's the nucleus of a regular hydrogen. So we call that hydrogen 1,1. Okay, so 1 is the atomic number, 1 is the mass number. Some hydrogen has a proton and a neutron in the nucleus. And again, one electron flying around. So this has a proton and a neutron, so it has extra mass in the nucleus. The atomic mass of this will be twice as much because the mass of protons and neutrons are around about the same. So this is hydrogen 2. And then we could have hydrogen 3. It's got a proton and 2 neutrons joined together. And again, still one electron at the top. So this is hydrogen 3. Okay, so 2 neutrons, 1 proton, total mass of 3 because we've got 3 things in the middle, and that's our 3 types of hydrogen. Now, this is the most common, and these two are fairly rare. The reason why these different isotopes of hydrogen are important is because they can be used for different things. They react exactly the same chemically. Because they have a single electron, they are going to react the same way that all hydrogen does. But you're going to get different water molecules, for example, that have an extra neutron present. So we call that heavy water when there's extra neutrons because the water has more neutrons in the nucleus. So overall, you have heavier water. Heavy water is used in many nuclear applications. So each of these hydrogens has the same number of protons in the nucleus. They all have 1 proton. And because of that, they all react the same because they have the same number of electrons. But in terms of their mass, that's different. So they have different physical properties, they have a different mass because of the different number of neutrons present in the nucleus. We're going to have a look at some examples in carbon in a second. So on the periodic table, you might have noticed, if you look at something like carbon, when you look at the mass number, you get 12.01. It's not a round number. The reason for that is because of the existence of several isotopes. Now, an isotope has the same number of protons as the regular atom, but a different number of neutrons. So if we look at carbon, there are 3 main isotopes of carbon. So there's carbon 12, carbon 13, and carbon 14. If we look at these symbols, it tells us a lot about what is in the atom, how the isotopes are different from each other. So the atomic mass up here, that tells you the number of protons plus neutrons. Okay, so in this case, the atomic number down here, so this is the atomic number, just call it the atomic number, that tells you the number of protons in the nucleus. So we've got the mass number, protons plus neutrons, and the atomic number gives us our number of protons. So from that we can figure out how many neutrons we have in the nucleus. So if we go over here, we have, so if we've got carbon 6, so we've got 6 protons. Then we do 12, the atomic mass, minus the atomic number, and that tells us how many neutrons are in this atom. So here's a question. How many neutrons in carbon 13? How many neutrons in carbon 14? So for carbon 13, we've got 6 protons again. And for carbon 13, we've got 13, so the mass number minus the atomic number 6, we've got 7 neutrons. So this is heavier. So carbon 13 is heavier than carbon 12. If we go down here, carbon 14, 6 protons. And again, 14 minus 6, that means we've got 8 neutrons. Now, why is this important? Most carbon that you see, if you burn a piece of wood and you look at the charcoal, most of the carbon atoms, if you could zoom in on them deep enough, you'd see would be this carbon-12. That's the most common form of carbon. There are small amounts of carbon-13 and carbon-14 present as well. They react exactly the same way as carbon does because they have the same number of electrons as carbon, so when we're doing chemical reactions we're looking at electrons. But they're slightly heavier and they also have some other different properties. Carbon-14 down here is radioactive. Its half-life is about 5,730 years. I'll talk about why that's important a bit later on. Now the way in which I've shown these symbols, where I've got the element symbol here, the atomic number down the bottom and the mass number at the top, that's a very common way of doing it. So we have X, Z and A. X is the symbol for the elements, Z is the atomic number, and A is the mass number. Okay, so that's a very common way of showing these isotope symbols. So let's go into a bit of detail about the isotopes of carbon. Like I said, most of the carbon atoms around you, in you, on the table that you're leaning on probably now, most of those are this carbon-12, so 6 protons and 6 neutrons in the nucleus. A very small proportion of the carbon atoms near you are carbon-13, so 7 neutrons, 6 protons, and then a very, very small proportion are carbon-14. Now, these small proportions here mean that on average, a carbon atom has a mass, relative atomic mass of 12.01. The relative atomic mass down here, or the atomic mass that we talk about, this is the average mass of an atom compared to carbon-12. So carbon-12 is this one, so that has a mass of 12, we call that 12. But carbon's overall average mass is 12.01 because we have this small proportion of these heavier naturally occurring isotopes of carbon. So if you pick carbon up, if you had 1 mole of carbon, we'll talk about moles a bit later on, 1 mole of carbon would weigh 12.01 grams, not 12.00 because we have this small proportion of carbon that weighs a bit more. We're going to talk about carbon-14 briefly. This is very handy in archaeology. Like I said, it has a half-life of 5,730 years. While you're alive, you're taking in carbon. So you're eating food that contains carbon. That carbon gets distributed around your body in things like the fats and the sugars and proteins in your body. And when you die, you stop taking in that carbon-14. And this carbon-14, because it's radioactive, it starts breaking down. So it breaks down into other elements that aren't as radioactive. So over time, the amount of carbon-14 in your body decreases, and after 5,730 years, you have half the amount of carbon-14 in your body than you would today if you're alive. So if I died, my body was buried, 5,730 years later, I would have half the amount of carbon-14 in my body than I do today. So archaeologists use this to date how long it's been since things have died, because when things die, they stop taking in carbon-14. So the amount of carbon-14 present decreases over time, and what they analyse is the amount of carbon-14 compared to carbon-12 in the organism's body, or the leftover remains of the organism, to figure out how long it's been since it's died. This can be used to date pretty much anything organic to around about 10,000 years, maybe 20,000 years at a stretch. Now let's talk about uranium. Uranium has 2 big isotopes that I want to talk about. Most of the uranium you dig out of the ground is uranium-238. So uranium-238, it's got 92 protons, so 92 protons, and it has 238 minus 92 neutrons, which is 146 neutrons. I didn't do that in my head, I calculated it before. So when you dig uranium out of the ground, most of it is this uranium-238. Now that has some uses. It's quite heavy. Uranium is quite heavy. It's a very heavy metal. But in terms of uses for nuclear projects, like in nuclear power stations or nuclear bombs, uranium-238 isn't as radioactive as uranium-235 is. So uranium-235, it still has 92 protons. But this time it's got the 235 minus 92 neutrons, NEU, spell it right, which is 143, I believe, 143 neutrons. So when you dig uranium out of the ground, most of it is 238, a very small proportion is 235. But this isn't useful if you want to use uranium in a nuclear power station or in a bomb. So you want to make more of the more radioactive substance because that's more likely to do the nuclear reactions required for your power station or your bomb to work. So what they do is they enrich uranium. They increase the proportion of uranium-235 to 238. All uranium is going to react very similarly. They have the same number of electrons. The difference between them though is uranium-238 is heavier than uranium-235. So what they do is they turn uranium into a gas and then they spin that gas around really, really quickly. The heavier gas flies out faster and further than the lighter gas. So the gas that contains uranium-238 that flies out of these things called centrifuges, goes further and further from the middle than the uranium-235 gas does. And what they do then is they condense that gas back, they turn it back into solid uranium, and that increases the proportion of uranium-235 to around about 5%. Once they do that, it's useful in power stations or bombs because you have more uranium-235 that's more radioactive, so when you're running your nuclear reactions, they run faster. The last isotope I'm going to talk about is americium-241. So I'm going to ask you some questions about it. How many protons are there in the americium-241 nucleus? How many electrons are around the americium-241 nucleus? How many neutrons are in the americium-241 nucleus? Okay, so americium-241, we have 95 protons. We have 241 minus 95 neutrons, which is 146. You can check my maths, I think I'm right. So 146 neutrons. The number of electrons in a neutral atom is equal to the number of protons. So 95 electrons around americium-241. Okay, so today on Flipping Science, we looked at what isotopes are, how to calculate the numbers of protons and neutrons given the symbols of isotopes, and some possible uses of isotopes. That's it for Flipping Science today. See ya.